So welcome to another lecture of Design of Machine Elements 1. In this lecture, we will be studying how to identify the critical cross-section and critical elements. The importance is that whenever you are designing any machine component, how critically it is loaded, you have to understand so that it will perform safely. So we have to identify where the cross-section is critical and where the element is critical. So we'll be understanding these terms in detail. So let's jump into this concept. So critical cross-section means in any member subjected to load, if you are considering where the cross section is located, where it is subjected to maximum load. When I am saying load, it may be force, bending moment or twisting moment. So whichever cross section within the member is subjected to maximum load, it is known as critical cross section. So once you are able to identify the critical cross section, then you will be looking for the stress distribution, so that within that cross section where the element which is subjected to maximum stress is located. First, for critical cross section, you are looking for the load, force, moment or torque. Once you are identifying that, then you will be looking for the critical element where the maximum stress induced is located. So for critical cross section, you are looking for the member load behavior, and for the critical element, you are looking for the element stress behavior. So we will be taking some example where you can identify the critical cross section and critical elements. For that, you will be taking the different types of load that we already studied, which are force, bending moment and torque. So you will be looking for the shaft subjected to force or axial load. The loading diagram is shown, both are same. So here we have to identify the critical cross section where load is maximum, where the axial force is maximum. So if you are taking two sections, 1 and 2, here if we are drawing the free body diagram with this 1 and 2 as well, you will be seeing that the same force is transmitted through both of the sections. So you can have a conclusion that the same axial load is passing through all cross sections, means all cross sections are subjected to maximum axial load, means all cross sections are critical. So this is the conclusion. So here for a shaft subjected to axial load, all cross sections are critical. So next you have to identify the critical element. So if you are taking any cross section which is critical, then where the element with the maximum stress is located. For that I am taking any of this cross section mentioned which is critical, then you will be having the force applied and you are having the resisting force developed. As a result of this, stress will be developed and it is of nature axial normal stress. And you already studied that for this kind of loading, all elements are equally contributing for resisting, so that the contribution per each element is same, or the stress developed from all elements are same. Means here all elements are critical. So for a shaft subjected to axial load, all sections are critical, and if you are taking any cross section, all elements are contributing equally, so all elements are also be critical here. So out of that element, I am taking a 3D element within this cross section is shown, where member is subjected to load P and the element is subjected to stress P by A, which is axial normal stress. So I will be extracting this 3D element which is shown here, where 3D element is shown and stress is acting along a single direction only, which is given by sigma equal to P by A. For simplicity, I will be representing this 3D element by a 2D element where the stress is given. So you can have for the stress distribution for a shaft subjected to axial load like this. So this is the axial normal stress distribution for a shaft subjected to the axial force or load. So where the stress is uniform. So here we have seen the where the critical section is and critical element is. So next we will be going for the next type of load, which is bending moment. First we will be looking for the, before that here we will be seeing the what is the maximum magnitude of axial normal stress developed. For a shaft subjected to axial force, load will be P by area, which is P by pi d square by 4, and which is you can represent it by 4P by pi d square. So this is the maximum normal stress. Now we will be going for the next type of load, which is bending moment, and first we will be discussing the constant bending moment. Here a shaft is subjected to constant bending moment. Loading diagram is shown. Here we will be looking for the where the cross section is, where the critical cross section is. Critical cross section means the section which is subjected to maximum load, and here load is of constant bending moment. So for that you will be drawing the bending moment diagram. The bending moment diagram for this loading will be of a rectangular, which means all sections are subjected to same bending moment. So here also you can get into a conclusion that all sections are critical as the bending moment is same throughout. So you have identified the critical section. All sections are critical. Next you have to identify which element within that critical section is critical or critical element. So for that you are knowing that the tension is coming on the upper side, compression is on the bottom fiber side, and the intermediate you are having a neutral axial or neutral layer. For getting the critical element rightly, you have to know the stress distribution. For that you can use the bending equation where sigma b equal to m by I into y, means sigma b is proportional to y, where y is the vertical distance measured from the neutral axis. For that you will be considering the any cross section which is critical. So where you are having a neutral axis which is coming here, so this is the neutral axis where the zero stress are occurring, because the distance from neutral axis to itself is 0. So distance will be measured with respect to the neutral axis. This is y, and you are observing that the maximum value of y is happening at this point, or the topmost fiber and the bottommost fiber. So these elements located here are subjected to maximum stresses. On the top side you are having maximum tensile, and bottom side you are having maximum compressive. So if you are taking any section which is critical, within those sections elements located at the topmost and bottommost will be giving you the critical element where stress is maximum. So for this case you have identified the critical elements. Next we will be extracting those or showing those elements here. This is the element which is subjected to maximum tensile stress, and this is subjected to maximum compressive stress. I am representing that element in a 2D way. So this is the element, and it is subjected to sigma bt, maximum bending stress tensile, and maximum sigma bc, maximum bending stress in the compression side. So the bending stress distribution here, you are having sigma b is proportional to y, so you are having a linear distribution with respect to the distance measured from neutral axis. So you can have the stress distribution which is shown in this way. So this is the stress distribution for a shaft subjected to bending moment, where bending moment is constant. So now you are having the same distribution at all cross sections, because for a shaft subjected to constant bending moment, all cross sections are critical. So you can have the same distribution at all locations. Now next you will be taking the case for a shaft subjected to variable bending moment. So in this case you have to first identify the critical cross section where the maximum load is acting. Here load is of bending moment, and if you are drawing the bending moment diagram, here bending moment diagram will be varying in a triangular manner. This you have studied in MOS, how to draw the bending moment diagram as well as shear force diagram. And if you are observing here, for a shaft subjected to a vertical load at the end, variable bending moment will be developed, and maximum bending moment is occurring at the fixed end. So which means the fixed end will be the critical section or critical cross sections. So once you have identified the critical cross section, next you have to identify where the critical element is located within the critical cross section. Since it is a bending moment, critical elements will be occurring similar to the previous case. The critical elements will be lying at the topmost point and bottommost point. So you can have at the fixed end section is shown, and the bending stress distribution is also shown. So which is similar to the previous case. So if you are observing, this is the shaft which is subjected to variable bending moment, and this is the fixed end where maximum bending moment is occurring. So bending moment is maximum at the fixed end means the stress will also be maximum. If you are taking some section here the bending moment will not be as maximum at this section. This will be much smaller, because if it is the load is acting at this point, then this is only the distance x. So P into x is only the moment acting at this section, which is lesser than this P into L compared to this fixed end. So bending moment will be lesser at this section. So the bending stress will also be lesser at this section. So if you are taking another section, here bending stress will be further lesser, and at the end bending moment is 0. So this section is 0 bending normal stress will be acting. And so this is the critical cross section, and the element located at the topmost and bottommost fiber will be the critical element. So this is the critical elements located at this point. So you have to calculate the maximum value of bending stress. You can use the bending equation m by I into y, where m equal to P into L in this case, where variable bending moment it is. So next for a shaft subjected to bending moment. I am calling that bending moment at M as M. It may be constant bending moment or variable bending moment. Whatever it is, the maximum bending stress at the location of critical element will be given by M by I into Y, where I is the moment of inertia for a circular shaft of diameter D, which is pi d raised to 4 by 64, and Y max is the maximum distance from neutral axis to the extreme fiber at the top or bottom, which is D by 2. If you are simplifying, you will be getting sigma B max, the maximum bending normal stress, equal to 32 M by pi d cube. This you should remember. You will be requiring this for solving problems in machine design in further lectures. So 32 M by pi d cube. So in last case, you will be taking the load, which is turning moment, twisting moment or torque. So this loading diagram shows a shaft subjected to this torque, and here you will be looking for the critical cross section. For that, I will be drawing the free body diagram by taking any cross section. So if you are looking similar to the axial load, here also all cross sections are critical, as the applied torque is transmitting through all cross sections. So all cross sections are critical in this case also. So once you are identifying the critical cross section, next you have to identify the critical element. For that, you will be requiring the stress distribution. For that, you will be using the torsion equation, where tau by r equal to T by J into G theta by L. So you can have tau is proportional to r. That means shear stress is proportional to radial distance from the center. So that you can have a conclusion that shear stress is maximum at the outer layer, where radius variable r equal to the radius of the shaft, or diameter by 2 of the shaft. So here, as these elements located at the outer surface are having maximum radial distance, all the elements located at this outer layer are critical. So for this case, any cross section is critical, and elements located at the outer layer are critical. So here I am showing an element located at the outer layer, where this one is the shear stress due to the applied torque or applied shear it is, and a reaction shear will be developed on this side, but shear stress will not be occurring in these two pairs only. It will be occurring always. There will always be a complementary shear stress because of the material to material or element to element bonding. This is showing the action and reaction shear. Along with this, because of the element to element bonding, complementary shear stress will be developed. This you have studied in MOS. So complementary shear stress will be developed in this direction. This is in such a way that the action and the reaction shear is trying to rotate the element in the anti-clockwise direction. For balance or for equilibrium, this complementary shear stress will be trying to rotate the element in clockwise direction. So complementary shear stress will be developed, and I will be representing this 3D element in simple way by using a 2D element, where the tau will be equal to T by J into R. So for this shaft also, you can find the maximum value of this shear stress. So all cross sections are critical, and the elements located at the outer layer are critical, where radius is maximum or capital R, which is D by 2. So you can find tau max as T by J. J is the polar moment of inertia, which is pi d raised to 4 by 32. Into, instead of r, here I am missing the d by 2 term. So here d by 2 will be coming. If you are simplifying, you will be getting tau max equal to 16t divided by pi d cube. Here d by 2 is there. So here you will be getting 16t by pi d cube, which is representing the maximum shear stress. So if I am taking any cross section which is critical, I can show this as a circle, and if you are taking any element located the outer surface are critical. So here the shear stress will be maximum, which since the load is applied torque is clockwise, so maximum stress will be happening in this direction. And if you are taking this element, the shear stress will be lying in this direction. So you can take any element. If I am taking some element here, the stress will be acting in this direction. So maximum shear stress distribution is, or torsional shear stress distribution is shown here. So I have shown some examples, different loading diagrams, where you can identify the critical cross section and critical elements. So here you have a summary. The different loading diagrams are shown, and the critical cross sections are also shown. The critical elements are shown, and the maximum stress corresponding to each loading is also shown. So you can refer this one. So hope you understood the concept of critical section and critical element. Thank you. We'll meet in the next lecture, where we'll be discussing about the combined loading cases.